Hi, my name is Matt Duff. I'm an application engineer here at Analog Devices, and we're continuing our stability series. We're going to talk about driving a capacitive load with an op-amp and why that makes an op-amp unstable. So if we remember from our previous series, the whole key is keeping our loop gain not equal to -1, or in other words, when we cross our 0 dB axis, we do not want 180 degree phase shift. We want a nice 20 dB per decade slope. So when we drive a capacitive load, what ends up happening is that we exercise the output resistance of the op-amp. So I'm going to draw in here, say R op. And generally we can ignore the output resistance of an op-amp because the feedback actually reduces the output resistance of an op-amp. But when we're doing stability analysis, we actually have to take into account kind of the raw output resistance of an op-amp, and actually that can be quite significant. So for a high power op-amp, maybe output resistance is 30 or 40 ohms, but for a low power op-amp, especially if it's rail-to-rail output, it can be in the kilo ohms, and so it can be rather large. And so what happens is that output resistance interacts with our capacitance here to form this RC feedback network. And so we end up getting, if we remember our beta equation, we're trying to calculate our beta, so we have this RC that's generating our beta, so we end up getting a roll-off just like an RC circuit with an extra pole. So if I superimpose that onto the gain of our open loop gain of our op-amp, which also has a pole, so here's the pole from the op-amp, here's the pole from our RC circuit, you'll notice that we get our 90 degrees phase shift, 90 degrees phase shift. So down here we have 180 degrees phase shift with our 40 dB per decade slope when we hit our 0 dB line, and we're going to be unstable. So what can we do to fix this? Well, the traditional method is to add a resistor in between the op-amp and the capacitor. And why does this help? Well, instead of having our RC circuit here, now we've got this circuit here. And what ends up happening is we still get a roll-off when we hit the combination of all these three components. So if this is my R op, and this is, I'll call this my R additional, then I form a pole, and that pole is I add these two resistors together and multiply by the C and multiply by 2 pi. So R, so 1 over 2 pi R op plus R additional all times C. And so I've got that pole there, but then what happens is as I hit the point where this capacitance is the same order of magnitude as this additional resistor I've added, I end up having a 0, and so I flatten out again. So this is 1 over 2 pi R additional C. So if I then transfer that and combine it with my open loop gain of my op-amp on this graph, that 0 ends up returning me to a nice 20 dB per decade slope. So I don't have this 40 dB crossing. Now I have this 20 dB per decade crossing, and so therefore I should be stable. Now, note that if I picked a teeny tiny resistance, then it would have taken a long time to do the switch. I would have had a long span here, and it would have been possible that my 0 might have come in underneath my 0 dB line, and therefore I would have still been unstable. So it is possible if you add too tiny of a resistance, then you can get an effect there. But generally your output resistance, your resistance you add doesn't need to be near as big as the actual output resistance of the op-amp. So that's why driving a capacitive load makes an op-amp go unstable. And next time we're going to talk about parasitic capacitance.